For the third lecture of the day, by Lars from Wisconsin Madison will tell us about swampland and cosmology. Please go ahead. Thanks.
Alrighty, Maddie, thanks a lot for the introduction. And also thanks a lot for inviting me to give some lectures here. So there's like a little bit of construction going on in the department here. So if there's like a bit noisy, I can try to, I'm not sure if I can try to do anything about it, but just let me know and then we can figure that out.
We don't hear anything, it's okay now.
Okay, that's nice. So yeah, so the subject that I'm going to tell you guys about in sort of these 4 lectures is Swampland in cosmology. So if you have during sort of the lectures, if there are any questions that come up that are not really addressed during the lecture itself, feel free to send me an email and we can always discuss afterwards. And to give you sort of an overview of sort of the subjects that I would like to discuss are the following. So today I'd like to give you some sort of introduction to cosmology, and in particularly set the basics for some inflationary cosmology, and also give a little bit of an introduction into effective field theory. And then we'll see sort of how to combine those 2 things and how we can sort of have an effective field theory approach to cosmology. And already I will give a bit of a hint of some of the perhaps issues that arise in sort of the standard picture of cosmology when we try to describe that in effective field theory. And that is, of course, where the Swampland comes in, where we're trying to understand sort of what constraints does quantum gravity put on these effective field theories that are supposed to describe cosmology. So then, roughly speaking, what we'll then see next tomorrow is I will talk about some of these cosmological Swampland conjectures. And so we'll see sort of what type of constraints can we put on cosmology from the Swampland. And of course, when we're thinking about cosmology, also the sitter space is a very important aspect of cosmology. So then in lecture 3, I think I will mostly sort of focus on the sitter space and its relationship with the Swampland. What can and what cannot we do in the sitter space, having Swampland knowledge in the back of our minds. And then I think sort of depending how it goes and how much time we have, I was planning in the last lecture to sort of present maybe some new ideas in cosmology, to sort of given the difficulties that we have in trying to unify the Swampland with cosmology, what are sort of the approaches that you can take, and then I perhaps would like to discuss some of the recent subjects that people have been working on. Sort of having said that, in regards of the level, I think there's some room for flexibility. So I will basically assume some familiarity with quantum field theory and general relativity and sort of combining the 2. Having said that, if you think that perhaps the level is perhaps too easy for you or you find it too difficult, feel free to let me know either during the lecture or by sending me an email, and then I will be happy to adjust. So I don't think the subjects are completely fixed yet. So there's definitely some room for flexibility. Or if you have particular subjects that you would be really interested in hearing about, also feel free to let me know. Okay. So having said that, I guess we can start with some introduction to cosmology. So I think sort of most of today's lecture will be based on the following reference, which is a book by Daniel Bauman and Lee McAllister, and they also have an archive version online, so it's really useful. So if you want to have some more details, you can also take a look at that. So I think sort of the modern cosmology basically starts with a a relatively simple observation. I mean, doing the observation is difficult, but its interpretation, I guess, is relatively simple, which is when we point our telescopes to the sky and sort of look at the energy density in the universe and how sort of the galaxies are distributed in our universe. Then at least at large scales, it seems to be the case that our universe is very homogeneous and isotropic. Of course, at smaller scales, you have like galaxies and everything. But when you sort of zoom out a bit, then at least a very good approximation, the universe is very homogeneous and isotropic. So what it means is isotropic, we look at the different directions. Things seem to be looking pretty much the same. Homogeneous is then when you look at sort of the matter distribution, then it also seems to be pretty much the same. But however, we know also that our universe is expanding. So let's say that we sort of draw two galaxies schematically that are separated by some particular distance. Let's say that they're separated by some distance x. And then if we now do some time evolution with some time t, when we draw the same galaxies again, we observe that those are further away. So they're separated now by a distance x, but then there's also a factor a of t, where this a of t we typically call the scale factor. So it sort of measures how far these galaxies have moved with respect to each other after some time t. So such a situation, when we think about space-time that is very homogeneous and isotropic, but is expanding, this is typically described by what we call a Friedmann-Robertson-Walker metric, or I guess we should also add Lemaitre to it. So FLRW, and then that metric looks the following. There's a time corner, then there's the scale factor that is appearing, and this scale factor only depends on time. And then we have sort of a free space here, and we're working in 4 dimensions. So sometimes it's useful to use slightly different coordinates, where we pull out the factor of the scale factor. So now we can write this as d tau squared. And this tau coordinates is typically referred to as conformal time, because now what happens is the metric is flat up to a conformal factor. Okay, so then when we have this expanding universe, of course, what happens if we now sort of think back about what happened in the past, and then sort of in standard Big Bang cosmology, we observe that when we go to the past, that this scale factor goes to 0. So what it means when the scale factor goes to 0 is that at early times, sort of in standard cosmology, there is a Big Bang sort of singularity. So the fact that at some point the scale factor goes to 0, it sort of means that there's sort of an initial time where the universe sort of was created in this Big Bang. So we can define our time coordinate in such a way that this happens at t equals 0. Then what this implies is that there's also sort of a maximum distance that, for example, a light ray can have traveled from the start of the universe. Because light rays follow null geodesics. What it means is that this maximum distance that this photon can have traveled is given by this conformal time. So delta tau is equal to delta x, and then be written as the following integral in terms of this regular time coordinate starting from t equals 0 to some time t. And we can write this in terms of an integral over the scale factor as follows. And what this defines for you the sort of this maximum distance, we typically refer to this as a particle horizon. And where I should mention that the parameter h that I introduced is defined in terms of the scale factor as follows, where the dot denotes a derivative with respect to this time coordinate. And what we can also do is we can introduce what is known as the co-moving Hubble radius. So it's basically this Hubble parameter, but then with an additional factor of the scale factor to sort of factor out the expansion. So what this co-moving Hubble radius tells you is that basically at some particular time t, let's say that we have 2 events happening at some time t, then this co-moving Hubble radius tells you was at a time where these two sort of events could have been in causal contact with respect to each other. So then depending if this co-moving Hubble radius grows or shrinks, sort of more events will be in causal contact with each other or less. So we'll draw a small diagram about that in a minute. So when we think about sort of standard Big Bang cosmology, then initially the universe was radiation dominated, and at some point that radiation got diluted because of this expansion, and we at some point got matter domination, and then finally it seems that today we're dominated by dark energy. And then when we look at sort of the evolution of the co-moving Hubble radius and these first two phases, they scale as follows with time. So when we think about radiation domination, the scale factor scales as t to the 2/3. So the way you can derive this is by looking at the Einstein equations with a stress function that describes matter, and then solve for the scale factor. So in cosmology, the Einstein equations are known as the Friedmann equations. So for radiation domination, we find that the evolution of the co-moving Hubble radius scales as follows: t to the -1/2. Importantly, it grows with time. And similarly, when we think about, oh, I made a mistake here. This should be 1/2. So for matter, it scales as 2/3. This scales as t to the -2/3, which also grows with time. So importantly, what it means is that this co-moving Hubble radius, at least in radiation domination and matter domination, grows with time. That is, when we go to the past, of course, the co-moving Hubble radius should be smaller. And this turns out to lead to a particular problem, and sometimes is referred to as the horizon problem. And that is related to the fact that what we observe in the early universe is this cosmic microwave background radiation. So let us draw a space-time diagram for how that looks. So let's see. So when we see that at some time t = 0, we sort of have our Big Bang singularity. Then what happens at some time after the Big Bang sort of happened at t = 0, we have the CMB that was released. So this is sort of this light from the early universe that was able to freely move to a transparent universe, and that is something that we can actually observe today using, for example, the Planck satellite. And then what we can do is we can, in this picture, we can draw the light cone, which can look as follows. Okay, this is not exactly 45 degrees, but that's just my drawing skills. So we can think of sort of that we are located here. Now we're looking back at the CMP. So we have some sort of light cone that is going back to the past. And then we can also draw the co-moving Hubble radius, which schematically looks as follows. So it grows during radiation and matter domination, and at some point becomes a bit smaller when dark energy starts to dominate. But now what's very important is that what we see happening is when we look at two different spots of the CMB that are sufficiently far separated on the sky from us, is when we look at the light cones here, we see that those regions were not necessarily in causal contact with each other. So we have this region, let's say this region here. We have one spot on the CMB that we observe, and then at some sort of angular separation from that, we see another spot on the CMB here. And those two regions in sort of standard Big Bang cosmology were not in causal contact with each other. So then you might say, okay, is that a problem or not? Well, it turns out this is a problem indeed when we look at sort of the observations of the CMB, what those tell us. So for that, I have a picture here. Okay, so here what we are seeing is we're seeing a sort of a photograph that the Planck satellite made. So what the Planck satellite does is it measures these photons that are coming from the CMB, and it can basically associate a particular temperature to that. And then, this image looks relatively isotropic and perhaps homogeneous. But what's important to matter is you see these different colors, which indicate the temperature difference from the mean. But this temperature difference is really extremely tiny. So when we look at the temperature difference that are indicated by the different colors, those are of the order of 10 to the minus 4. So when you have your thermometer and it's not sensitive to temperature difference of 10 to the minus 4, you would just see you would see the same temperature. So you would come to the conclusion is that these different patches in the CMB, they were extremely homogeneous and isotropic. So they basically, up to these small corrections, they have the same temperature. And that's, of course, is quite puzzling when we think about it, is when we look at the space-time diagram, is when the CMB was released, these two different patches that are almost exactly the same temperature up to very small differences, they were not in causal contact with each other. Which of course puzzling, because why would they have almost the same temperature if they were not in causal contact with each other? Who told them that they would have this particular temperature? This is typically referred to as the horizon problem. And what's even more is when you also look at these fluctuations, and it also turns out that these fluctuations, so they're these different from the mean, that those are also correlated at these super horizon scales. So there's clearly something going on where you would expect these two regions. It seems necessary that somehow they knew from each other and they would have needed to be in causal contact. So this is one of the problems with standard Big Bang cosmology before people introduced inflation that needed to be addressed. And maybe before I go on to tell you perhaps how this could be resolved, I should maybe stop for questions. Feel free to, if you think this stuff you already know, feel free to let me know, and then I can try to speed up or change subject a little bit. Okay, but if there are no questions, let me just continue. So the question that you need to address in cosmology is how to explain these correlations. Or said differently, there are two things that you want to explain, I guess, which is why are these two regions so homogeneous? Why do they have almost the same temperature without being in causal contact? And how could it be that these correlations are also, these fluctuations are also correlated at super horizon scales? And one way how you could explain this is to just say, well, there must be some process, some other energy density that dominated the universe at early times, such that it was not the case that these regions are causally disconnected, but there was some causal connection between the two. And then in terms of the metric, how you would realize that is basically what you need in the early universe is you need to have more conformal time. As you want to make sure that you push this Big Bang singularity further to the past, in such a way that you allow these regions to be in causal contact. So what we want to have is some type of energy density that decreases the co-moving Hubble radius. So in order to decrease the co-moving Hubble radius, how do you do that? Well, when we take the definition of this co-moving Hubble radius, we find that having r dot to be negative, what this means is that we need the following inequality to be true. So we want the co-moving Hubble radius to decrease. So we can nicely capture this inequality in the following parameter, which is known as the first slow roll parameter, which we typically indicate by epsilon. So we want minus h dot divided by h squared to be smaller than 1. So this is one condition that you need to satisfy in order for this co-moving Hubble radius to decrease. It also turns out that in order to really solve this horizon problem, you also want to make sure that there's this period where the co-moving Hubble radius decreases, the depth was sufficiently long enough. So that can be captured by a sort of second slow roll parameter, which we typically call eta, which is basically the derivative of the first slow roll parameter epsilon. So these are sort of the two conditions that we need to satisfy. And then, of course, we want to ask ourselves the question, sort of what type of matter can realize such a phase of co-moving Hubble radius decreasing. And of course, one example that you might already think about is that does something like this is when you have a scale factor of the form e to the ht, which would be the scale factor of exact de Sitter space in the limit where h dot is going to 0. And what we'll see is that whatever this period of domination was where the co-moving Hubble radius decreased, it seems to be very closely related to this sort of de Sitter limit. Okay, so let's assume that we have such a phase of where the co-moving Hubble radius decrease. Then what does the corresponding space-time diagram look like? Let me draw that on the next page. So now let me again draw this light cone. So we are located here. Now what happens is that our previous Big Bang singularity was located somewhere here. The CMB is slightly further away. Maybe it's useful to write this in terms of conformal time. But now what happens is that because now we are introducing some additional conformal time. So some extra tau, some extra conformal time, is what we now can do is when we now draw the light cones from the CMB. And also the co-moving Hubble radius, which then looks schematically something like this. This is RH. But now what we see happening here is that in the past, if we have enough conformal time in the early universe, we now find that there's causal contact. So the light cones sort of the different patches of the CMB, they now overlap in the past. So this would be a possible explanation why these different regions are so homogeneous, why they have almost the same temperatures, and how it could be that these correlations that are happening in the CMB at here and here, why they are correlated with respect to each other. Okay, so now of course you might wonder, okay, this is a very nice idea, Lars, that you're telling me about. We just need some additional conformal time. Of course, you want to make sure that you have some sort of realistic model that can also generate this. So then you need to basically ask yourself, what is the equation of state of the matter that generates this additional conformal time? And I already alluded to this a bit by saying that something like the de Sitter space seems to be able to generate this. So when we think about it in terms of the Einstein equations, let's say that we take the assumption that the stress tensor takes the form of a perfect fluid. So then there is some energy density rho associated with the TT component of the metric. And then when we look at the spatial coordinates, so I runs, I guess, from X, can be X, Y, Z, so sort of your standard flat space. Then there is some pressure, and there's also the scale factor that appears in the stress tensor. Then when we look at the Einstein equations and we play around a bit with its different components, you can derive what is known as the Friedmann equations. So it tells you how the evolution of the Hubble parameter goes as a function of the energy density and pressure of the fluid. So then H dot is proportional to rho plus P with a minus sign, and then H itself squared takes the following form. Now remember that what we want to achieve is we want to make sure that we can have a slow parameter epsilon that has the following property. So we want to make sure that minus H dot whoops, this is a typo, that minus h dot over h squared, that is smaller than 1. Okay, so what we can do is we can now use the Friedman equations to express this in terms of the rho and p parameter of the fluid. So what that means is that we want epsilon, you can write this as follows: 3/2 1 plus p divided by rho, and this to be smaller than 1. So in terms of rho plus p, what this means is that we get the following situation. So we want to make sure that rho plus 3p is negative in order to generate this period of, I guess we can already call it inflation, where the co-moving Hubble radius decreases. So let's say that we take the energy density to be positive, then one sort of interesting observation is that you can already see whatever this sort of fluid is, it needs to violate the strong energy condition. So if you're a formal GR type of person, you might be interested in knowing something about these properties of this fluid in terms of its equation of state. Okay, so this is just sort of a relation on rho and p. But then, of course, you might want to have an explicit model. So sort of the simplest way to, or at least a very simple way to generate such a fluid, or to have such a fluid which obeys this particular equation of state, is a slowly rolling scalar field. So when we look at the stress tensor associated to a scalar field, we get the following. And then I'll tell you what we mean by slowly rolling. There are some derivatives acting on phi. And there's a potential energy. So what do we mean by slowly rolling scalar field is if we draw the following figure of the potential. There's some scalar field phi that can, at least sort of without looking at these fluctuations, what we do is we also take the scalar field to be homogeneous and isotropic, so it only depends on the time direction. And what we're interested in is sort of a situation that looks as follows. If we have a scalar field here that can be evolving sort of towards the bottom of the potential, then we want it to be slowly rolling, so it has to be the slope of the potential sort of needs to be sufficiently shallow enough in order that the kinetic energy of this scalar field does not become too large. Because then we can see that we can obey this condition of this equation of state where we want rho plus 3p to be negative. So when we compute this energy density and pressure associated with the scalar field, we get the following. So we have, for the energy density, it's just, as you might expect, the kinetic energy plus the potential energy. Then for the pressure, it's the same kinetic energy, but then there's a minus sign in the potential. So then you see in the limit where the potential energy is dominating over the kinetic energy. So this is sort of the regime by what we mean by slowly rolling, that the kinetic energy is sufficiently small with respect to the potential energy, then we find that rho plus p is approximately -1. So what this means is that this basically behaves as a cosmological constant. And I guess that sort of makes sense, because let's say that we have this scalar field that is exactly stationary at the bottom of the potential, then this is precisely a cosmological constant. And now we're just sort of sprinkling some additional ingredients on top of that, that we want to have this slow evolution. And basically the reason why we want that to be true is because we know that this period of inflation eventually has to stop. So there needs to be some sort of natural exit. And how to do this And one way to realize this is when you have this slow evolution of the scalar field, and at some point, perhaps you reach a minimum, or this slope becomes too steep such that this inflationary period stops. And then again, so we can see sort of how this de Sitter limit is realized. So it's basically what I just said. Let's say that we take phi dot to 0, so the kinetic energy vanishes. Then, of course, we're again in the regime where we have an exact de Sitter space. So then sort of the takeaway lesson, I guess, of what I just told you about how to generate this period of inflation is that when we want to understand if you want to understand the early universe, then what is important is that we sort of understand the Sitter space, or this sort of slowly evolving situation that looks like the Sitter space, which we typically refer to as quasi de Sitter space. And that's quite interesting because there are many aspects, especially when we start to think about sort of how to embed such a situation of inflation or de Sitter space into quantum gravity. There are a lot of problems that we face, which makes it a very interesting subject to work on, because there are really big challenges that we need to overcome in order to really understand sort of physics in our own universe. Are there any questions about sort of this picture of inflation and cosmology before I move on to effective field theory? Okay, I think not. Okay, so what I will now do is I would like to introduce you to some sort of the basic concepts of effective field theory that will be important for us. And then after that, I will sort of combine that with this sort of inflationary point of view. So how can we describe this period of inflation also from effective field theory? And sort of what are the problems that you face when trying to do that? Okay, so the intro to effective field theory. So the notion of effective field theory sort of arises when we, it's very intuitive in the sense that, let's say that we want to describe some physical phenomena. And typically physical phenomena, they happen around a particular energy or a particular distance scale. So let's say that you want to describe sort of what happens in this room. Then I guess the human scale is the relevant scale that you want to look at. And scales much larger or scales much smaller are sort of less relevant for describing your physical phenomena. So, so let's say we want to describe physics at some energy scale that are much smaller than some particular energy scale lambda, which we refer to as the cutoff scale. Then what we can do is we can use effective field theory. So sort of to give you a concrete example of when effective field theory would be useful, let's say that we are a particle physicist and we want to do some scattering experiment, and sort of the canonical ensemble example that you can look at where effective field theory is useful is when you look at, for example, scattering of a neutron and a proton that are exchanging a W boson to create an electron and a neutrino. So this is sort of, if you have access to, I guess, standard model physics, you know sort of how the standard model works. This is the Feynman diagram that you would write down. But let's say that you're interested in energies much smaller than the energy of the W boson. Then you might write down a theory that looks slightly different. So formally, what you say is that what you can do is you can integrate out the W boson. So sort of, at least to sort of first approximation, what that means is, let's say that you have your Lagrangian that contains the W boson. Then what you do is you use the equation of motion of the W boson to remove it from your theory. And then what you're generating is a so-called effective theory that contains this effective vertex, where we are no longer seeing the W boson, but instead we have a theory which has this sort of contact interaction. So this is what we refer to as the effective vertex. So this can be very useful if you sort of want to look at a slightly simpler system at these energy scales much smaller than the W boson. So then you can write down your theory with respect to these 4 vertex operators. But then, of course, this is something that is can be very useful, especially when you don't understand or you're unaware of what's happening precisely in the UV. So let's say that you're not aware of the existence of the W boson, as physicists were, I guess, in the earlier 20th century. Then you can try to model this interaction just by writing down sort of all possible operators that are consistent with the symmetries. So I will come back to that in a moment. So of course, if you're interested in quantum gravity, you might want to take a similar approach to quantum gravity. Let's say that we're not really well, I guess it's fair to say we don't fully understand sort of what is the correct theory of quantum gravity. So you might take this effective field theory approach where we don't really understand sort of what this UV dynamics is. But let's say that we do know that, and we're thinking about like a string interaction. Then we can write down a similar effective vertex. For say, okay, there are some closed string exchange that looks as follows. Then let's say that we're at energies much smaller than the string scale. Then we can write this sort of as an effective graviton vertex. And of course, so when we're at energies much smaller than the string scale, it might be very useful to just work with respect to this effective theory, such that we don't need to worry about sort of complicated UV physics. And then so the basic notion of EFT, you can construct it in 2 ways. So what I just told you about, where we sort of already know the UV theory and then integrate out massive states to create an effective theory, that is typically referred to as a top-down method. So this is where you know the UV and you want to integrate out states. But I guess more often than not, when EFT is really useful is when you are not precisely aware of what's happening in the UV. And in that case, it's more useful to use a bottom-up approach, where we just say, okay, we don't know precisely what the UV theory is that leads to our low energy physics. So what we're going to do is we're just going to write down all operators in our, let's say, our action that are consistent with the symmetries we think the theory should have. At least up to a fixed mass dimension. So in a moment, I will give you a precise example that I guess clarifies sort of how this works. Okay. And of course, what is necessary for this EFT framework to make sense is that these 2 approaches agree. So what you can do is you can, let's say that you take some particular simple model with some heavy state, you integrate it out, you get some effective theory. Then what you can do is you can check that if you take this bottom-up approach where you're saying, okay, I don't know precisely what UV is, I just write down all these operators that are consistent with the symmetries that I think my problem should have. Then you can check that these 2 approaches agree. Okay, so yeah, so maybe an example of this. Let's see, an example of how such an effective action looks like. So what you would do, let's say that you're interested in sort of the EFT for a massive scalar field. That we know that at low energies, we have a Lagrangian that looks as follows. So we have a kinetic term, and we have a mass term. And now what the sort of EFT approach tells you is that now, in addition to sort of these low energy operators, what you should write down is basically an infinite tower of possible higher dimensional operators. So you have a sum over I, where I runs basically to all the operators that you're considering. So very schematically, what this means is you have some operator O, some index I that depends on the scalar field. And now this is suppressed by this energy scale below which we're working, which we refer to as the cutoff scale. So in general, in EFT, you have these infinite towers of operators. Infinite tower of operators. Then, of course, what we're interested in describing a process up to some particular energy scale. So let's say that you just want to consider the leading operator. Then you just want to make sure that you're including the term that is least suppressed by this cutoff scale. So that has sort of the lowest mass dimension. So some terminology. So this C of I, we typically refer to those as Wilson coefficients. This OI was the high dimensional operator. And this lambda is the cutoff scale that we're working with. So in the example of the W boson that I just gave, there the cutoff scale will be the mass of the W boson that you integrate out. So your theory is only sort of sensible below that energy scale. Okay. So let me now give an example of how that comes about, where you integrate out a particular state and generate an effective theory. So let's say that we're looking at the following action of a scalar field that is non-minimally coupled to gravity. So then the action that we would write down is the following. So we have some Einstein-Hilbert term. And then we have this non-minimal coupling psi to the Ricci scalar. And L is just some length scale in order to make sure that this Wilson coefficient psi is dimensions. So that's typically useful to do. Okay, then we have a kinetic term for your scalar field, and we have a mass term. Okay, so now what we want to do, we want to assume that the scalar field is heavy, and we want to construct the EFT that is generated by integrating out the scalar field. So then what we can do is we can look at the equation of motion for the scalar field, which then takes the following form. So it's sort of your standard Klein-Gordon equation of motion, but then there's this additional term due to the non-minimal coupling of the scalar field to the Ricci scalar. So now having this equation of motion sort of to leading approximation, what we can do is to integrate it out, is we can substitute the scalar field as expressed from the equations of motion. So what it looks like is the following. So when we substitute this scalar field into the action, then what we have to do is we have to expand in low energy. So what we want to make sure is that we're working at energies squared, I guess, that are much smaller than the mass of the scalar field. So when you substitute the scalar field back into the action and you perform this expansion, then you find the following effective action. Here in this case, we're just interested in sort of constructing the leading high dimensional operator. But in general, there will be an infinite tower of terms that are generated. So now we just have, there's no longer a scalar field, so we just have this Einstein-Hilbert term, and then we have this first correction, which takes the following form. And of course, there are now terms that we are suppressing that would scale as higher powers of the mass. So now what we're seeing is we started out with a scalar field non-minimally coupled to gravity. We used the equations of motion to integrate it out. And that's where what we're left with is this action that has this higher dimensional operator. So we see it's, in this case, suppressed by the mass of the scalar field. So that is the cutoff scale in this theory. Is proportional to these Wilson coefficients. And I guess if you count its mass dimension, I think I'm not made a mistake, that this is a dimension 6 operator. So this is sort of, I guess, a simpler model to work with in effective field theory than our original models that we started with, if we're just interested in energy scales that are smaller than the mass of the scalar field. And now let me relate sort of this question a bit to the swampland, because what is at the heart of the swampland? So I guess what was at the heart of the swampland, I just gave you this example where we couple this scalar field to gravity. But then the question that you can ask is, what are the constraints? That quantum gravity puts on this EFT, or I guess generically puts on effective field theory. And you already see like a little bit of that showing up in this particular example. Because what happens here, for example, these Wilson coefficients, you know is proportional to xi squared over m squared. So you already see that its sign in this case is positive. And of course, when we know where this theory comes from, that's not so surprising, because we probably don't want to try to integrate out the tachyon. We want to make sure that the mass squared is positive. But if you're just an effective field theory person, then you would have written down this Wilson coefficient, and a priori you wouldn't have known sort of what its sign is. But now having this UV information where this particular model comes from, we know that it better be a positive coefficient. So this is just a very simple example where we see that sort of consistency in the UV. It seems to constrain the form of the EFT in the IR. But this is a very generic principle in the swampland, is that we want to sort of understand without looking at perhaps particular UV details, to understand what are the constraints, for example, on the Wilson coefficients of operators that appear in the EFT. And I guess we'll come back to that in some next lectures. Okay, so this was just this particular EFT model. So now we can also try to ask ourselves the question. So in the beginning of the lecture, we talked about this inflationary cosmology. Can we also write down an EFT for inflation? Which seems to make a sense, seems to be a sensible statement, because I told you that inflation could be generated by this slowly rolling scalar field. So in the spirit of EFT, what we could do is we could write down an action with a scalar field, perhaps corrected by some leading high dimensional operators, and then see sort of if we can still do inflation with that. So when we do that, there's a particular problem that becomes revealed. So let's consider an effective field theory for inflation. And maybe to try to not confuse you too much, typically when people say the EFT of inflation, they mean something slightly more general, where they're not necessarily thinking about the scalar field, but just take a more generic approach. Here, what I mean when I say EFT for inflation, I basically mean writing down an EFT for the slowly rolling scalar field. So it's a slightly more restrictive sense in which I use the word. So remember, what do we want to do with inflation is when we think about these slow roll parameters, we want to make sure that those are small. So previously I wrote them down in terms of this Hubble parameter, but now when we're thinking about sort of this single field slow roll model of inflation, we can also express them in terms of the potential, where now this apostrophe is a derivative with respect to the scalar field of the potential. So I want to make sure that epsilon is small, and we also had a second slow roll parameter eta, which basically ensures that that the inflation lasts long enough to sort of solve this the standard cosmological problems. So we also want to make sure that this is small. And of course, what you now see happening here is that this term that appears here, that is basically the mass of the scalar field or the mass of the inflaton. So in this single field slow roll model of inflation, what we want to make sure of is that the scalar field is sufficiently light in order to generate an appreciable period of inflation. So then let's say that the low energy action of the scalar field is given by the following. So we have our kinetic term, we have a possible mass term where the mass should be light. And we have, let's say that we have some constant terms on constant energy density in this model. Then, as we said, when eta is sufficiently small, what it implies in terms of the Lagrangian is that the mass parameter should be sufficiently small. And I guess there should be another dimensionful factor in order to make sure that the dimensions add up. Okay, so let's say that we now want to take this EFT approach, and we're saying, okay, this is just the leading terms that are describing this model, but there could be all kinds of UV effects that we don't know about, and we want to write down, sort of parameterize those using these high dimensional operators. So then one operator that you could write down is a particular dimension 6 operator. So we add to the Lagrangian an operator of the following form. So this is just as a particular example. So C here is a Wilson coefficient. There can be a low energy potential that appears, and then this is multiplied by phi squared over lambda squared. So when we want, so what typically happens is because lambda is the cutoff scale, and typically what happens is that this term is sufficiently small. However, when we take into account this particular operator, we know that it's, although the effect of the operator seems to be sufficiently small because it's suppressed by this cutoff scale, is now when we look at what its correction is to the slow roll eta parameter, we get the following. So the correction to eta is proportional to the Wilson coefficient. And then there's a term m Planck squared over lambda squared appearing. So sort of depending on the precise details of your inflationary model, sort of how large of field excursion do you have in phi, what can happen is that this term, because it's m Planck squared over lambda squared, we typically want to make sure that our cutoff scale is below the Planck scale at least, and typically much smaller. And this can give a very large and dangerous correction. And it's dangerous in the sense that it would spoil our slow roll conditions, and we would not generate a sufficient period of inflation. Okay, so what does this tell us? So we started with this sort of nice idea of inflation. We just taken simple EFT approach. And it seems that immediately sort of the first operator that we could write down in an EFT perspective seems to give a large and dangerous correction. So then you might wonder, how can we prevent such a situation? So of course, one way to prevent such a situation, if we have some mechanism by which to forbid sort of these large and dangerous corrections. So the resolution necessarily seems to be, or in a very natural way, seems to be symmetries. are there symmetries that we can invoke in order to forbid such large and dangerous corrections? But in order to answer these questions, can these symmetries be there? It seems to be necessary that we have some knowledge about sort of what's happening in the UV, if those UV theories could respect such symmetries. So this issue or this problem is typically called the UV sensitivity of inflation. Meaning that although what we were interested in was sort of constructing a low energy action that did not depend too much on UV details, we see that in the inflationary context or in cosmology, this sort of bites us, and we're drawn to the situation where we do need to talk about sort of some particular UV effects. And in particular, can we realize these symmetries in order to forbid these large corrections? And so sort of the takeaway from this is that we need to understand, in order to understand this early universe cosmology or inflation, we need to understand quantum gravity. That is, of course, where Swampland comes in, because now sort of the hope is, of course, that sort of Swampland conjectures, they will sort of guide us to understanding, can such symmetries be realized? Can we forbid these large corrections? Or are there sort of alternatives that we need to explore in order to describe our early universe? And I think I'm almost exactly out of time. So maybe I should stop here. I'm not sure if there's time for more questions. I left some room for it in the middle. But if we have not, feel free also just to email me, or if you have like particular suggestions that you want to hear about tomorrow. So with that, thank you.
Thank you.